really good of you to join us on a Sunday for this session, and we're really excited to present to this group. I think we have a very strong values alignment with the effective altruism movement. So we're hoping to really build some relationships here, and we're looking forward to, as James said, your comments and your some good discussion as we go through our presentation today. So my name is Kirsty Gogan, and with me is my co-founder Eric Ingersoll. I'm going to hand over to Eric now to tell you a bit about TerraPraxis.
Thanks, Kirsty. And again, thank you guys all for being here. We really founded this kind of this organization in a similar spirit to what we imagine the sort of goals and approach that effective altruism has, which is that we really felt that the decarbonization discourse was missing key things that were really important for us to succeed, both succeeding with decarbonization and succeeding with building a planet that is a just and safe and prosperous place for everyone to live. And furthermore, not only were those things kind of missing from the discourse and missing from the kind of climate world, but the solutions that were being developed also, not surprisingly, didn't reflect any of those kind of additional values and that additional vision that we saw as being necessary. So our organization was founded
sorry, Eric. No, you tell me when you're ready to go.
Yeah. And so just organizationally, we have organizations in the UK and the US, and we're active globally. Next slide. So this kind of gives you an idea of what is of the challenge that's not really being met. And this shows that projections for the sort of mainstream projections for the future of the global energy system suggest that we will still be using a very high percentage of fossil fuels, even in the 2040s and the 2050s. And Kirsty and I had an amusing little discussion about this graph when we were preparing this presentation, because it's from 2018 and it's now 2022. And our conclusion was that this graph was optimistic about declines in fossil fuel consumption and use. And actually they're higher than this graph shows today. But the key thing is that there are very large segments, such as gas-fired power plants, gas for industry, coal-fired plants, and liquid fossil fuels, which are applications that our global economy really depends on today. And we don't really have things to substitute, fully for those applications. And that's why energy, fossil energy use in those segments continues. Next slide.
Yeah, and sorry, Eric, one little insert, which is that what we're actually really looking at here is a 4-degree trajectory of warming. That's
what this means.
That's kind of what it means.
And if we want to prevent that, we have to repower all the coal plants with something that doesn't create emissions. We have to replace the flexible gas plants with some kind of flexible generator that doesn't produce emissions and doesn't fund Putin. We have to replace gas for the industrial applications where gas is used for high temperature heat. We have to find a way to replace liquid fossil fuels in all their applications. And we have to do this while growing the energy system for the developing world, which may mean a 2 to 3 times increase in the energy consumption on the globe. And we have to do this in a very short time. Next slide. So, as I mentioned earlier, we founded the organization because we felt that many of the parts of the problem were not being represented in the kind of simplistic dialogue around how to solve the climate problem. And this was leading to a lot of discussion about climate solutions, which really just came across as what we would call technology push. You know, solar's the solution. How do we just jam more solar into the power sector? Let's just mandate that the utilities have to buy it. Let's just, you know, close down coal plants. So kind of very, very sort of, you know, almost like you went and just asked some energy people, what should we do? But you didn't somehow take account of the broader set of factors that are really necessary for real solutions. So we call these things climate solutions 2.0, and what we're seeing now with the challenges that we're facing in the energy transition, as we start to take the energy transition more seriously, we're seeing a lot of obstacles. We're seeing the collapse of the wind industry in Germany. We're seeing opposition to renewables projects all over the United States. You know, we're seeing that the amount of gas that was sort of presumed to be in the system providing flexibility and dispatchability for the power sector is a cause for a lot more expense and financial risk and geopolitical risk than you know, maybe people were thinking when they designed those strategies. And in the US in particular, we've seen how communities that have their predominant employment based around fossil fuels extraction or fossil fuel conversion into electricity can be just dead set against the transition. And this has really deadlocked the kind of progress that we were all hoping to see under the Biden administration. And so, and furthermore, these sort of political and social risks also, you know, there's also a whole set of technical risks that we have to deal with. And one of the big ones in the United States and in other places is the amount of transmission that needs to be built if we're going to use the high renewables decarbonization strategy. And so we feel that we should be designing, not that we shouldn't continue to try to do those things, but that we should really be designing a portfolio of solutions that actually take these constraints, these problems as requirements that you have to solve with the way you design the solution. And we summarize those as costs, speed, scale, space, like how much space does this take up, what kind of supplies, how much strategic minerals and metals and various things, other things that the supply of which could become a constraint, and also the political support that you need in order to implement these things at large scale. So we have to design solutions that kind of build in all of that, not just say, oh yeah, we're going to put 2 terawatts of renewables all over the Western United States. Hope you like it, which is a little bit kind of the way it's gone here. So we on the left, you see a little diagram that says, we really start by looking at climate risk, like which sectors are not decarbonizing, where are all those future emissions projected to come from, where are we in danger of seeing very large demand growth, such as in the developing world, and so forth. Then we kind of resolve that into a set of what we call a problem definition, which is precise enough to give us a set of requirements for a solution. And then we work on the kinds of technologies and deployment systems and other business and economic factors that could enable a plausible solution to that problem. And then we do multiple rounds of stakeholder engagement to make sure that we've understood the problem and the kind of political and social landscape that this is, you know, would be deployed into. And that includes, you know, consulting with large businesses, with, you know, political entities, as well as, you know, local communities and other people. So that's an approach to designing these climate 2.0 solutions. And this presentation, we're going to talk about one of those. And I suggest, you know, I hope you can see elements of this in the solution that we talk about.
And Eric, maybe just in a couple of sentences, describe the Iowa case study, just to sort of shine a light on the risks.
Yes, so one of the things about the risks to the energy transition, and our organization and our team spends a lot of time looking at this because it's really important for designing solutions that are going to work. And so we've done a case study on wind in Iowa, and this case study came about when we were supporting a U.S. decarbonization modeling exercise, which a whole bunch of organizations were involved in, including many that are probably supported by you guys, people like Third Way and Clean Air Task Force and other folks that we work very closely with. The modeling team was showing us the projected resource available, renewable resource available in various states in the US. And they projected that the total available resource, the technically available resource of wind in Iowa was over 600 gigawatts, which is, the total US grid is 1.5 gigawatts. So, you could look at that and go like, yay, we just have to build a lot of wind in Iowa and we're like part of, most of the way there. But when I started looking online, I saw that there was a lot of stories about public opposition to wind in Iowa. And so, we started a project to look at how much of Iowa was actually available, politically and legally available to build wind on. And this analysis was not included in the modeler's approach to modeling the amount of wind resource that could be built in the United States. And because of the way Iowa permits wind at a county level, we were able to look at the laws for every county, each of the 99 counties in Iowa. And we found that over the last 15 years, 2/3 of the counties in Iowa had laws restricting or preventing the development of wind projects in that county. And in some cases, these restrictions were, significant but not prohibitive. And in other cases, they looked like restrictions rather than prohibitions. But, effectively, they were so restrictive that nobody would build a wind farm there. So, and this is not being modeled in to the future projections in the decarbonization models about how much wind, can be built in Iowa. And this is true for many of these Midwestern states. And we also supported a project with Clean Air Task Force and McKinsey looking at Germany in the same way, and found very similar conclusions, that if you didn't only look at the technical issues, but you actually looked at the legal restrictions, there was very little onshore wind potential left in Germany today. And, so we have this gap between these projections which say, oh yeah, don't worry, we'll build 1.5 terawatts of wind in the United States. And then the reality on the ground, which is there's this, not only is there sort of public opposition, but there's real legal constraints now coming into being. And so this is what we mean when we are talking about how the risks to the transition. So Kirsty, do you want to take it over from here?
Oh, sure. Great. Yeah. So we have one of our theories is around the Impossible Burger, which many of you may be familiar with. It's a plant-based meat substitute that looks like a burger and tastes like a burger, and you can buy it in every Burger King across the land. And it doesn't really require any behavior change. And so, the kind of intractable problem of, politicians not wishing to advise their citizens to eat less meat is solved or being solved by technology, by a drop-in substitute that's equivalent in terms of cost and performance. So it achieves the benefits without requiring behavior change. And we think that given the scale and the urgency of the transition, the extent of the sort of transformation of the global energy infrastructure across not just the electricity sector, but across liquid fuels and industry and heavy transport and so on, that's needed within an incredibly challenging timescale, 28 years now to 2050, when, you know, we really have to have, you know, bent the curve, as we showed in the IPCC report. In order to achieve that transition within those timescales, we're going to need impossible burgers for climate. We're going to need drop-in substitute fuels, and we're going to need those fuels to be cost competitive with the fuels that we use today. And ideally, we need to be repurposing as much of our existing infrastructure as possible. And that's, you're going to see these kind of principles in action in the case study on repowering coal that we'll go to now. So let's look at the kind of global picture of coal, which, you know, is the largest single source of carbon emissions globally, representing almost half of global carbon emissions. Even in countries with old coal, like in the United States and Europe and Canada, it's really, really difficult. It's a really challenging proposition to expect that we'll just close down those plants. It's not like a simple, oh, they're producing emissions, therefore we have to shut them down, because as we've been sort of describing, you know, all of this infrastructure sits within complex social, economic, political ecosystems. And there's a lot of opposition to the prospect of closing down these coal plants. Jobs and tax revenues that people depend upon, and the prospect of just abandoning those assets is really devastating for communities. And then in addition to that, almost half, in fact, more than half of the global coal fleet is less than 20 years old, on average about 14 years old. So in addition to those, you know, social and economic and political challenges that we're all familiar with in Europe and the United States and Canada, there's also the issue that actually many of these countries with newer coal plants really depend upon the electricity generation. And there's more than $1 trillion of capital invested in that coal fleet that has yet to be recovered. So our view, and this isn't just our view, you know, we're talking with you know, many global experts who are very deep into this issue and very concerned about this issue, believe that it's entirely unrealistic to assume that we will just abandon these assets before the end of their useful life. And that presents a real challenge, because that coal fleet, 2 terawatts of coal, that, you know, anyone who's clear-eyed about it would expect to still be operating by 2050. Just that fleet will completely demolish our carbon budget for the power sector. So we're going to turn now to, you know, a solution that we're designing for that 2 terawatts of coal. And here you see the vision of a repowered coal plant. You can see the transmission there in the background, which of course, as Eric was saying earlier, is, you know, really going to be necessary, that we repurpose the existing transmission as much as possible in order to de-risk the transition by, you know, at least reducing that dependency. But it also, you'll see, as you can see, we're proposing to reuse as much of the coal plant infrastructure as possible. Now that has many, you know, environmental benefits to, you know, not just demolish that, you know, those buildings, but actually to continue using them. But it also means a certain level of like for like transfer in terms of jobs and economic performance. In fact, we would anticipate that these repowered coal plants will not only be cheaper to operate than before, create many more economic and high-skilled job opportunities for communities, but they'll actually be even more profitable to run than before, because they'll be running without emissions, they'll be dispatchable, flexible generators, able to complement wind and solar, and therefore they may actually be producing more electricity than many of the coal plants do today due to the cost of fuel and the emissions. Oh, got a blank slide there. So we're going to describe to you the sort of the process. Oh, actually, I have one. Yeah, I had a slide which was sort of explaining why this is not happening already. And some of you may have heard about repowering coal as an idea. And, you know, for example, there's an advanced reactor company in the United States that's building an advanced reactor on a former coal site in Wyoming. It's Bill Gates' company TerraPower and a joint venture with GE Hitachi, and they're building, their joint venture is called Natrium. And they have incredible levels of public support, community support, which is fantastic. In fact, Wyoming is changing the law to lift a moratorium on nuclear to enable this project to go ahead. So you can see that there's tremendous pull from the political and community stakeholders for this great solution to create, you know, an operating plant without emissions that can, you know, produce economic prosperity for, you know, decades more. But that's just one plant. And, you know, wonderful though that is not going to be achieving the scale that we need to actually repower all of these coal plants by 2050. So here you see on the outer circle, the kind of the virtuous circle that we need to create, which is that we need to make it cheaper and faster and less risky for coal plant owners, for project developers, for investors to even really consider doing these projects. And then we need more, I can't read the bottom on there. We need more projects, and we need more suppliers. And we're going to describe to you how we're going to create this virtuous circle that will enable this process to be much more efficient and enable all the plants, not just one of the plants, to be repowered. So here you can see a coal plant being repurposed and some of the kind of key attributes. Now we have a sort of a relatively small number of key design principles that will enable us to achieve the sort of speed and the standardization and reduce the risk in the project and lower the cost. And firstly, you see that we're reusing much of the coal plant infrastructure. So we're already de-scoping the project from being like a full new power plant that you have to build to reusing a lot of the existing power plant infrastructure. Essentially, we're just decommissioning the coal boiler and replacing the heat source. So in order for that to work, you need a heat transfer and storage system. And that is going to be designed to match the steam and heat requirements of the existing coal plant. There'll be a range. In fact, there's quite a big range. But that's what this heat transfer and storage system will enable. It's a bit like, it'll be a bit like a USB plug for the coal plant. We need to have a really efficient approach to designing and delivering the buildings that will enable a very efficient regulatory process. We'll actually show you how we'll be taking as much of the nuclear safety grade components out of the nuclear safety system and being able to be delivered through commercial buildings. And then we need a standardized advanced heat source system within a standardized building, which is really critical because we're not sort of picking a advanced heat source technology right now. What we're designing for is a range of heat sources. So we'll be using standardized interfaces to enable standardization within the building system and therefore being able to accommodate a range of advanced heat sources as they come to market. And then finally, seismic isolation. Now, one of the key things that really drives redesign each time you build a new nuclear plant is the seismic conditions at the site. And these vary very widely. In the UK, for example, we're building a nuclear plant at Hinkley Point. And although there's an intention to replicate that design on a subsequent site, which would represent huge savings in terms of, you know, reduction in design engineering and regulatory processes because the plant will have been licensed before. Unfortunately, you can't actually replicate to another site because of the seismic conditions being different. So this means that you then have to reopen the regulatory licensing process and you have to do more design engineering. And essentially what you are doing is creating uncertainty around the cost and timescales and the schedule for your project. So seismic isolation means that once you've certified your design once, then you should be able to replicate that many, many times at any different site.
It's critical for scalability.
Right. So standardization, you're going to hear that word a lot. So as I said, we're going to be standardizing our design to enable the heat source system to be able to match a wide range of energy and heat requirements. to accommodate a range of advanced heat source technologies, and also to be delivered against a range of site layouts and local requirements. So these are the constraints that we've identified to being able to really deliver at the scale and the speed that's required to repower 2 terawatts of coal by 2050. And that's what we're designing for. So Eric, do you want to do this one?
Sure. So what we were showing is as a method for basically bringing a new heat supply to an existing plant and being able to use as much of the plant as possible. Our initial estimates are that this is a savings of at least 30% over the cost of building a new plant, but it may be significantly more than that in many instances. That's sort of like the most conservative number that we came up with. It's really enabled by this kind of modular approach to the design that you see here. Next slide. And Kirsty mentioned earlier that we're attempting to remove much of the kind of specialized gear from the building, the nuclear grade buildings. So one of the challenges you have in a traditional nuclear project, which is what makes them big and complicated to design, is that you sort of, the nuclear engineers have allowed large parts of the plant or all the plant to become something that is part of the safety case and is part of nuclear oversight, nuclear regulation, and nuclear quality assurance. So what we've done is we've gotten our design team to identify the systems that could be essentially moved out of that envelope to reduce the envelope for what is really required to be part of the nuclear safety case. And actually the generation 4 heat sources that we're looking at also enable a lot of this because they use a much more passive and sort of physics-based approach to safety rather than relying on active safety systems for that. So we're basically taking that a lot further and using kind of standardization process so that many of the supporting systems might be standard across all the advanced reactors. And this creates additional savings, additional reduction in design work and cost reduction.
Yeah, the analogy that we like to use is that if you imagine that we're building a kitchen with a slot where the microwave goes, and then the wide range of microwave oven suppliers can put their components, their high value heat source component into that slot.
And this extends all the way to making the reactor building standardized. And so here you see a graphically demonstrated a standardized, a modular, configurable building, reactor building, with a place for the microwave, right? With a place for the heat source. And the sort of the unfortunate reality is today that getting a power plant designed, a nuclear power plant designed for you is like inviting the microwave designers, the microwave engineers to come in and design you a microwave and a kitchen to go around it. And that leads to very high costs, non-standardized stuff, and nobody would buy a kitchen like that if they were.
And a totally fresh, picture for the regulator each time as well, which creates a lot really of complexity and risk. And yeah.
So this is just showing what I was referring to earlier about moving the systems outside of if they're not part of the safety case, standardizing them and moving them outside of the nuclear grade buildings. So the purple color is the nuclear grade building, and the commercial grade buildings on either side of it are shown here in green. And this means they can be much simpler, faster to construct, cheaper. Next slide.
Off the shelf.
And then this is just showing the approach to the standardized advanced reactor building and how we can accommodate different reactors in the building by making the building longer or shorter, but which does not change the profile or the kind of components that you need. Those concrete components would be precast components that would be made at an offsite precast factory. And here it just shows that you can accommodate different reactors by making it slightly longer or shorter. And but you're not actually changing anything fundamental about the design of the building.
And one thing to say about this is that, you know, we're developing this approach in parallel with the demonstration and commercialization of the advanced heat sources, the advanced reactors that, you know, are expecting to be demonstrating and operating towards the end of this decade, late 20s, early 30s. And the beauty of this is that we can get on with the design process for the kitchen that, you know, will accommodate the microwave oven, that will accommodate the heat source. And we can also get on with developing the other associated tools, the financial model and the design assessment tool, the design tool, the site assessment tool, and so on, which we'll describe in a moment, to enable coal plant owners to potentially be evaluating hundreds of sites for repowering and getting ready to to develop those projects while the advanced reactors are being commercialized, and then choose when they come to market which one they actually want to have in their building system. But this means that instead of waiting for the advanced reactors to commercialize in, you know, the late 2020s and then starting to look for sites and starting to figure out the supply chain to deliver them and all that stuff, what we're doing is really accelerating the mass deployment of these technologies by priming these markets.
Yeah, and the other thing that's useful about this standardized building system, it's useful here to think about IKEA. That what IKEA do is develop a set of products, and then they develop these global supply chains for the products, and everything that you get in that box when you order the IKEA product is manufactured. And when they design it, it's designed for the manufacturing facilities and the supply chain that they have, and they achieve low cost through that kind of very rigorous design for manufacturability process. That is not how nuclear plants are designed today. So we are partnering with an engineering and design firm that specializes in creating kits of parts for enabling a variety of buildings to be delivered with that kit of parts. And so everything you see in here is a manufactured component that is then turned into those buildings. And that's how we can achieve potentially achieve the rate of deployment that's necessary, hundreds of plants per year. And these would all be things that would be available through a standard existing set of suppliers that could be qualified to deliver them. On the seismic design, again, as Kirsty mentioned, this enables standard, it allows you to use the same building design in each place, and all you have to change is the process for the design of the isolation system. And that's something that we're working on with the Nuclear Regulatory Commission right now. So as Kirsty was mentioning, what this design system and building system that we're developing, it's really a set of tools to help potential power plant customers for repowering projects get started and get through these stages of the development process. So is there a viable project here? If it looks like there's a viable project, how do we define what the project really is? Are we going to repower all the coal units? Are we going to repower some of them? How much will it cost? How much space do we need? And then, the pre-construction is you need detailed documents. You need design documents so that you can engage with regulators, you can engage with the supply chain and so forth. And further on into construction, you need to be able to manage that project and ensure quality and track that you are on target and so forth. So we're working with industry to develop and qualify a set of tools that will be available through the cloud to enable coal plant owners to actually get started on this process and to do it very cost effectively. So one of the other things that the standardized kit of parts enables is it enables what are called like configuration tools. So it enables a kind of automated design of the plant, of the configuration of those components. So when you know that you have, say, 5 different advanced reactors and a variety of different plant layouts, you can essentially create the design tools that will automatically create those designs out of those components in response to, kind of setting the parameters for the project. So we're working, and Bryden Wood, our design partner, is one of the world's experts and leading firms in doing this kind of automated design process, which they already do extensively for the data center sector and pharmaceuticals manufacturing. So we're right now in the process of developing a screening. The first phase of this is a screening tool that will enable coal plant owners to essentially look at their sites, kind of get some basic ideas about the projects and the requirements for those projects, do some preliminary financial analysis, and basically kind of get started on their project development process for their fleets. As we go through the next 2 or 3 years, we will be adding the project definition and pre-construction tools to this offering of services. And ultimately, next slide, this will be, because we know what the plants will be made out of, they'll be made out of these components, you can then provide a lot of additional value in the management of construction and ultimately even in the operation of the buildings. This is really filling a kind of a market failure right now. If a coal plant owner wanted to do a repowering project today, they would be forced to spend hundreds of millions of pounds or more in assessment, feasibility studies, design. There are no standardized designs that are available today. So that means you have to go and get someone to do you a bespoke design. When they're doing a bespoke design, you don't know how the licensing authority, the nuclear safety regulator, is going to respond to that design. And so you don't know if you have a project that's actually going to work. And what we found is most of these coal plants, there isn't a large budget sitting somewhere in the company that owns it to spend, 50% or even 2 or 3 times the value of the coal plant on figuring out whether you have a project. So in that case, we really think what's going to happen is that these coal plants will continue to be operated because of the political and social realities, and there won't be an easy way to convert them. So this project is really addressing that market failure. And
because each new nuclear plant right now is a one-of-a-kind project. So each of the kind of key stakeholders that you see represented here on this slide have to be engaged in what essentially looks to them like a one-off process. The supply chain need to design for deliver against a bespoke specification. The advanced heat source vendors need a special plant built for their particular kind of heat source design. The assemblers will never have built one before, so each project is a first of a kind that requires learning and investment in skills and capability, and often a lot of additional design engineering work, all of which represents additional cost and risk to the schedule. And then you have the utilities that have to take a risk each time, and the investors, which also have to take a risk, and the customers, and ultimately the regulators are in a very difficult position because they are having to evaluate the safety case for, a new, often very complex, bespoke power plant each time. So again, cost and risk to schedule is, the critical issue that we're seeking to address through this set of cloud-based tools enabled by the design for manufacture and assembly process for the majority of the heat source building. So this is our sort of our roadmap ahead. As Eric said, we're developing the screening tool right now to enable coal plant owners to begin evaluating their sites. using the tool that's being built and hosted by Microsoft. And then ultimately next year and later this year and next year, we'll be developing the conceptual design. And we're working very closely with a number of different regulators in a number of different countries to ensure that, you know, the design philosophy that we're approaching this with, the seismic isolation, the thermal energy storage, which delinks the heat source from the power island, you know, these design principles are sound and they're supported by, you know, by the regulators as we go through our design process. And then ultimately in 2024, we hope to be moving into the detailed design stage with a view, as we were saying, to be ready for mass deployment around the 2027 timescale. And we actually suspect that the current commercialization timelines for the advanced reactors that are being developed right now could in fact be greatly accelerated by this approach, by de-risking all of these challenges, creating real market pull, enabling, well, delighting the regulators, and by, you know, enabling the customers to come forward and pull these into being. So here is our finally the kind of the key partners that we're working with. You can see that KPMG is listed here that we haven't mentioned, but who we're working with and developing financial tools to enable coal plant owners to evaluate the benefits of repowering. Bryden Wood, our design and engineering firm, Microsoft, who are developing the cloud-based tools with us. And then we have colleagues at MIT working on the heat transfer storage system, and Professor Andrew Whitaker, who's at the University of Buffalo and is really one of the world's leading experts on seismic isolation. So we do have really a world-class team leading this project. And if you look at the Bryden Wood website, as Eric said, you can see, you know, an incredible demonstrated track record of these approaches in other sectors, which we think are really highly transferable to nuclear. These include highly regulated, very complex sectors, achieving astonishing amounts of standardization and, you know, real design for manufacture and assembly with automated design and digital tools. Reducing, you know, cost and risk to schedule, and reducing design time critically from years, even just to weeks. So that's how we think we can repurpose 2 terawatts of coal plant infrastructure to enable, you know, the continued supply of clean emissions-free energy, but without the emissions. And I think we should stop there and allow some time for questions. I don't know if there's been any.
There's been a couple in the chat, and I've got one as well. But also, other people either put your hand up or you can obviously put a comment in the chat. But I would say, okay. I guess first thing, thank you so much. I guess the first thing that comes to my mind is like about the advanced heat sources. I guess it seems like from what you said, it's mainly going to be nuclear, and I guess is that the case? Can we primarily like small modular reactors? You're thinking, and to what degree are you working on like the R&D side of that as well to kind of hurry the whole thing along?
So the short answer is that the leading advanced heat sources that are in the commercialization programs in the US, Canada in particular, are based on technologies that have achieved kind of a high degree of demonstration already. And what the SMR companies, so for example, sodium cooled reactors have been operating for decades in various locations, including demonstration reactors and some sort of commercial demonstrators. Same with high temperature gas reactors. So really what is going on in these startups that we hear about, or these small companies that are commercializing these, is really the productization of these technologies. So it's not an R&D problem. It's not like, oh, how do we make a fuel that does this, or how does this coolant work, or it's not that. It's how do we make a repeatable 300 megawatt manufacturable thing that is, you know, not too complicated, that achieves these cost targets, that can be licensed easily, and so forth. So it's really working on delivering these things as a product rather than as a kind of a, you know, R&D design problem.
But Eric, that also delivers the heat, right? And yeah. You know, James, we're actually very we talk about advanced heat sources because it's the attribute that we want. So if that can be delivered with supercritical, super hot rock geothermal, ultimately with fusion or fission, you know, what we need is a very small environmental footprint, a very high capacity factor, and we need high temperature heat. So this isn't applicable, for example, to small modular reactors, light water small modular reactors, because they don't produce the temperatures that are required for the supercritical steam that you need in the coal plants. So those are the constraints, and it's like, give me the heat source, and then we can make this work. And right now, yeah, it looks like it's the advanced fission.
But I think the other thing that we would
to market.
We are very interested in a kind of this tech neutral approach, and we really see the goal here as creating demand for advanced heat source development activities, right? So this is going to help any company that is developing an advanced heat source technology, because we're by enabling these customers to start the project development process for what is ultimately a $4 trillion market for repowering the global coal fleet. This is going to, you know, for people who, for example, have been funding advocacy for advanced nuclear, one of the frustrating things is that, you know, we have a large amount of fossil plants in the world, and they could be, you know, replaced or repowered with these advanced heat sources, but it's not easy to sort of demonstrate that there's a market for that technology, and therefore there's a lot of kind of need to do policy support and government funding and all that to get the advanced heat sources sort of through the product development phase.
Yeah, and actually, let me give one quick example of that, which is also linked to a question here in the chat about you know, the developing economies and how they can participate. And I think this is a really important question, because as we said in the beginning, almost half of the global coal fleet is less than 14 years old, and the majority of that is in you know, developing economies that really need that energy and have, you know, unrecovered investments that, you know, it'll be very difficult to walk away from those. And actually, we've been hearing that the Asian Development Bank is currently reconsidering its position on nuclear to actually consider financing nuclear projects. And part of that is driven by this opportunity to repower coal plants, because right now, what you might have heard at COP26 are stories about how we finance the decommissioning of these coal plants, but there is no plan for how you're going to replace that energy. It's very unlikely and difficult to expect that we would replace that, you know, 90% capacity, you know, gigawatt scale energy with wind and solar, for example, which require massive amounts of geographical area and have much lower capacity factors. So they're just not a like for like replacement, and you lose all of the socioeconomic benefits associated with those plants. So right now there's financing mechanisms being developed to mothball the coal plants in these countries, which means basically sort of shutting them down, but not demolishing them, not destroying them, but keeping them potentially available for reuse in future. And this repowering coal opportunity could be it.
Cool. Yeah, thanks. That makes sense, and it's very exciting, seemingly. And also one kind of follow. I think you said you missed a slide on like why it wasn't happening already. I guess I wonder if you can touch on that point, because it seems like almost too good to be true. It's like, wow, this is all great, but like, how come it's not already kind of rolling ahead?
I don't think we have a snappy answer to that question. You know, I mean, there with a lot of these things, there are, you know, that kind of question in a way is sort of a like, you can ask that question about a lot of good things that aren't happening in the world.
There's no incentive. We're filling a total gap.
No, I think,
here.
But
there's like no strategic incentive by any actors to do this. The advanced reactor vendors are in a kind of mindset that this is how we've always done nuclear, and so we have to do it that way. Everybody is in that same mindset that we've always done it this way, so we have to do it this way. And so the joy of a philanthropically funded, civil society-based project being led by, crazy, intense
Innovators.
climate hawks like us, is that we're able to just like break it all back down and figure out like what are the reasons why this isn't working at the scale and the cost and the speed that we need, and then design it from the ground up. And so but there hasn't been civil society based organizations paying any attention to the potential for nuclear technologies, or there have been a small number of them, but there hasn't been funding, and there still isn't really enough funding. There's funding.
Let alone
So
funding.
This is a very new. Yeah, and Founders Pledge are total courageous leaders, I would say, in this regard. And so is the effective altruism movement too, more broadly. So, really thank you for enabling.
And
this
I want to
kind of
just add one little rejoinder there, which is that the sort of economist way of understanding why something isn't happening is typically described as a market failure. And so when you have market failures, you have something that looks like it makes sense, but there are reasons like institutional or incentives or other problems that are not causing this thing to happen. We believe this is a classic example of a market failure for the reasons that Kirsty was outlining, and that we need, and that philanthropic funding is one of the ways you can address market failures. And we believe that as we get through 3 or 4 years of our project, we will actually solve this market failure, and there will be large amounts of capital from the investment world and from the business world that will flow into this space and begin to transact and begin to repower the global coal fleet.
And you'll notice that our approach is not like, Kirsty and Eric going into a kind of, smoke-filled room with wet towels on our heads, trying to sort of figure this out, although there is quite a lot of that as well. But we're talking to all of the key stakeholders right from the beginning, and listening and iterating and designing to their requirements that we hear. And so the goal is to, our methodology is to come up with these very radical, innovative solutions, but to sort of, do that in lockstep with the critical actors who are going to be the decision makers or the, delivery partners, so that, we're de-risking our approach every step of the way.
I wanted to answer Matthew's question about how do we get over the basic problem of renewables being 3 to 8 times cheaper. So the first answer is that they're not 3 to 8 times cheaper. There are some very expensive nuclear plants which are being built in the way that Kirsty described. Hinkley and Flamanville and some other plants. Most of the nuclear plants being built in the world are radically cheaper than these, in the sort of $1,000 to $3,000 a kilowatt range, and they produce power that is very, very similar to the cost of wind and solar in those markets. People also tend to use the lowest priced renewables in the world, so say solar in Abu Dhabi, and compare it to the most expensive nuclear plant in the world, say Hinkley. But if you compare the solar that's available in most places to the nuclear that would be available if you built those plants the way they do in China, you find that they're not actually that different in cost. And we're experts in this topic, and we keep track of all of this. And so there is a kind of systematic distortion in the way these costs are represented, that some of us who are a little bit more in touch with the data find quite annoying.
Secondly, but it's also the system. Oh, yeah.
Well, what I wanted to say is that we're looking at advanced nuclear plants, which are going to be much simpler and much cheaper. We're looking at delivering them with a manufacturing model, which will make them even cheaper and faster to deliver. And we're talking about reusing the coal plant infrastructure, which knocks at least 30% off the capital cost, and possibly more. And we've done detailed projections of these costs for ARPA-E in the United States, and we estimate that these plants will be able to produce power for about $35 a megawatt hour, which is without tax incentives. And when you look at solar projects in the United States without tax incentives, they can do that. They can do it for about that, and wind can do it for a little bit more than that. And so, and those projects are not dispatchable. So they're not, those wind and solar projects will only produce when the sun is shining and when the wind is blowing. And the grid needs a large amount of stuff that can turn on when those conditions are not true. And when we look at what the costs of providing that dispatchable energy are, those costs are well above $35 a megawatt hour if you start adding storage to any of those other technologies. So this will be a very cost-effective system, but it's also important to say that we don't see this, we see these plants with their thermal energy storage included as incredibly good complements to a large renewable build out. So this is not instead of doing renewables. This is going to enable a lot more renewables because you won't be constrained by factors like needing to put storage on all the renewables. And so this is so you're saying that that nuclear is 8 times cheaper than solar in China? I don't think so. I really think they're
Louisa's got her hand up, so maybe I'm also conscious of time. So maybe Louisa, you can it was a question or comment, and then maybe we'll slowly wrap it up.
Yeah, first of all,
I think the key, I just want to mention that the key thing is what really is going to make the difference in the coming decades is how do we create the lowest cost system that meets the requirements for a clean energy system.
Great.
And that's cheap.
Louisa.
That's more than just the cost of energy.
Yeah, thank you for the great talk. I'm very grateful for the work that you're doing. I think it's awesome. My question is, you mentioned one example with wind energy, and you said that many do not take the projections do not take the restrictions into account. So I'm wondering, why are they not doing this? Are they not aware of this? Or do they not want to be aware that we're not going to solve everything with renewables? So, and how are people reacting when you confront it with them?
This is a really good question. So I think what has started to happen, and I think many of us in the climate space are feeling this, that there's a real sort of, it's a dawning realization that we're not making the progress fast enough that we need to be making. In fact, the contrary is true. We're not making any real progress in terms of emissions reduction. And then in addition to that, what we're finding is that in places that have very ambitious programs for building out renewables, such as California and Germany, and we mentioned the Iowa case study earlier, which have incredible potential. They're sunny and they're windy and they have very strong supportive political, and public support for the transition, and they're still not getting it. They're still not getting there. They're not able to build fast enough. They're not able to find enough sites. Transmission is a barrier, and public opposition increases the more that you build. So I think the key thing here is just because it's cheap, it doesn't mean that you can build it. And that idea that just because it's cheap doesn't mean that you can build it leads to questions about the need for more feasibility analysis. We need to sort of interrogate our energy systems models for feasibility. And you can put hundreds of gigawatts of wind and solar into your energy system model that looks like it's getting you to zero, but we need to start actually measuring what the rate of deployment would be required, for example. So if you need to build 10 gigawatts of solar per year every year to meet your 200 gigawatts of solar target in California, 9 out of 10 projects won't get built, which means that every year you need to have 100 gigawatts or 90 gigawatts of solar in the pipeline, which means you need project developers, you need sites to be evaluated, you need to have the associated infrastructure in place. And if you fail to get your 10 gigawatts built this year, then you're going to have to build more next year. And that rate of deployment, that speed, is a consideration which is starting to gain some traction as, you know, energy systems modelers, and we're working with some of the largest energy systems modelers in the world who are coming to us to have these discussions about how we close the gap. Essentially, they're recognizing increasingly that there is a very significant gap, and not just in the electricity sector, which should be the low-hanging fruit, the easy one, but we, you know, at least we have some ideas for the electricity sector. We're not really able to still push those through. The scale of infrastructure builds is just, you know, and the sequencing of that build is extremely challenging. But then we really don't have good answers for other parts of the economy, for the other 80% of our energy use, such as liquid fuels for heavy transport and industry and so on. So I think it's happening, and I'd expect to see this trend of, you know, the need for a much more realistic interrogation of what the models are telling us. Come back to us in 1 year, and I bet we'll be able to benchmark a radical change in the way that we're thinking about these challenges.
Yeah, Kirsty, if I could just add to that, I mean, the fundamental sort of cultural reason that that's not happening is that the models that are used to do the modeling for net zero are based on production cost of electricity. So they are based on sort of an LCOE calculation. Some of them do real-time analysis. So they figure out like what would be the cheapest thing to produce in that hour. And the result is that you end up with a bias towards low cost, non-dispatchable generation in your model. Most of the modelers do some kind of very high level assessment of feasibility. So for example, the modeler that I mentioned in the Iowa case study, they had taken results from the National Renewable Energy Lab estimates for renewable potential in all of the different states in the United States, and they were using some version of those numbers. But what we found was that those were based on what's called technical potential, not some kind of more grounded understanding of all the factors that would constrain building those projects. And I think one of the reasons why these social constraints are not, or these kind of zoning constraints are not taken into account, is because and this is a good reason, it's not bad faith by the people doing the assessments, but they believe that, you know, if we really wanted to do something about climate, we could change those things. So they're not really like a fundamental obstacle. They're a socially imposed obstacle, which is a choice that people are making. And but I think, unfortunately, so we agree that it is a choice that people are making and that we could change it. The problem is that if we count on changing it and we don't have a strategy that's broad enough with enough technological depth and enough different options for reaching net zero, it's very likely that these things, which are social choices, will actually end up being pretty serious constraints to achieving what we need to achieve.
Great, cool. I think that's probably all we have time for. And yeah, sorry, we've run over slightly, but I think that was really nice ending in terms of, yeah, definitely you want to plan for the worst and make sure we have all the solutions in toolbox rather than banking on, we'll overcome these regulatory hurdles. Totally fine. So yeah, that's a really good way to finish. But cool. Thanks so much, Eric and Kirsty and everyone for coming. I will send out an email with all this recording and maybe some various links. Maybe that case study in Wyoming sounded really interesting, so that could be something I put forward. But otherwise, thank you all so much for coming, and hope you have a nice rest of Sunday evening. And yeah, thank you again, Eric and Kirsty.
Thanks, James.
Everyone, bye-bye.